Today, myself Sruthy Krishna is from the Department of Electronics and Biomedical Engineering here to present a seminar on the topic electrostatic capture and on-chip lamp amplification for airborne pathogen detection. The seminar has been guided by Mr. Shinu MM, Assistant Professor of Electronics and Biomedical Engineering Department. So this is a brief overview of my seminar. Firstly, I'll be going through the abstract following the introduction about airborne pathogens and its detection technologies, and I'll be going through the key research papers I have gone through, and we'll be mainly focusing on the objectives of the seminar and classifying airborne pathogens and its detection technologies. In the seminar, we'll be mainly focusing on two main topics, that is electrostatic capture and on-chip lamp amplification, and its experimental and simulation setups, performance analysis, etc. And further, I'll be concluding my seminar with a future outlook and conclusion. So, electrostatic capture and on-chip lamp amplification is a hybrid technique for airborne pathogen detection. It will improve early diagnosis of air by enhancing aerosol sampling and rapid genetic amplification. In this seminar, I'll be covering the evolution of airborne pathogen detection methods, focusing on its shift from the traditional era methods to modern real-time detection technologies. The detection techniques are classified based on the sampling method, amplification mechanism, and system integration for public health applications, and I'll be specially focusing on the design and working of electrostatic capture for virus capture from the ambient air, also the integration of lamp amplification on microfluid chips for fast and specific detection without thermal cycling, also uh, highlighting its role in infection control and real-time surveillance and pandemic preparedness. So, as we know, airborne pathogens such as virus, bacteria, and fungi can spread quickly in closed spaces like hospitals, airports, and offices. So, in the figure one illustrates the transmission risk of airborne pathogens in enclosed microenvironments. As we can see, in closed environments, the ventilation will be poor and the pathogens remain suspended in the surface, increasing the risk of transmission. The figure 2 illustrates the typical dimensions of airborne pathogens. As we can see, the pathogens compared to the size of pathogens, virus is a smaller particle and they can spread quickly in air. These curves in the diagram illustrates how different pathogens of dimensions settle in different respiratory tract regions. So electrostatic sampling with LAMP will enable a fast real-time pathogen detection, which is simpler and quicker than RT-PCR. The figure 4 illustrates how ESP prevents the spread of viruses, and figure 5 illustrates the schematic diagram of on-chip LAMP amplification for airborne pathogen detection. So these are the key research papers which I have gone through while preparing for my seminar. The first paper is highlighting the integration of electrostatic capture with on-chip lamp amplification for airborne pathogen detection, and the second paper illustrates the recent advances in the on-site airborne pathogen detection technologies. The third paper is mainly focusing on the electrostatic receptors design and its efficient removal for aerosol and airborne viruses. And the fourth paper is the reviews the recent developments in measurement of airborne viruses. It discusses the detection challenges, etc. So the key objectives of my seminar are evolution in detection, like its shift from the slow culture method to rapid detection technologies to a portable nucleic acid based systems with a higher speed and accuracy, electrostatic capture, that is charged fields efficiently collect airborne viruses which will whose performance depends on charging mechanism and system design, on-chip lamp amplification, ultra-fast sensitive DNA RNA amplification on microfluid chips for real-time point-of-care diagnostics, and application in future critical for hospitals, HVAC systems, and public health surveillance, boost performance, boost pandemic preparedness. So the airborne pathogens are mainly classified into three: virus, fungi, and bacteria. We have familiarized them earlier in the introduction slide, as we have seen that viruses are very small particles and they can spread quickly in air. Fungi and bacteria are larger particles compared to uh, viruses. So, overview of detection technologies. We will be briefly familiarizing the detection technologies from the early era to modern era, and I will be going in detail about the emerging detection technology, that is electrostatic capture and on-chip lamp amplification. So next, let's familiarize briefly about the early era detection technologies. Early era detection technology consists of passive settle plates, microscopy and staining, filtration, and impingers. Passive settle plates is a simple low-cost method. It consists of a petri dish in which a nutrient agar will be deposited, and the microbes can be settled into it. Heavier airborne particles are settled into the plate by gravity, and after exposure they are incubated for the microbes to grow. It does not provide how much volume of air has been captured. Next is the microscopy and staining. It is a traditional method to identify and count the amount of microbes collected on the filter or the slides. Stain enhances the visibility of microbes under the microscope. Next one is a filtration method, active method, using a pump to draw a known volume of air, and impinger draws air through a narrow jet into a liquid medium, trapping particles by inertia. So next, let's familiarize the modern era detection technologies. Modern era detection technologies are classified into three: high volume air samplers, immunoassays, and nucleic acid amplification. So high volume air samplers are air samplers that capture a large amount of airborne pathogens quickly. So it consists of impactors and cyclones. Impactors separate particles by inertia, whereas cyclone separates particles by centrifugal force. Next one is immunoassays. It consists of ELISA and LFIA. ELISA is enzyme-linked immunoabsorbent assay, and LFIA is lateral flow immunoassay. So, immunoassays are lab-based tests, specific binding between the antigen and the antibody to detect the pathogens. Like if a pathogen is present on a sample, it binds matching antibody. Their binding is made visible through color change, fluorescence, or a signal. Next one is a nucleic acid amplification technique. It consists of qPCR, RT-PCR, and RT-qPCR. So, RT-PCR, that is reverse transcriptase polymerase chain reaction. Firstly, it is used for the RNA viruses. Uh, the RNAs are isolated, then it converts RNA to the copy of DNA, that is cDNA, using reverse transcriptase, and amplifies cDNA by polymerase chain reaction and detects RNA viruses. It does not measure the quantity. Second one is a quantitative real-time polymerase chain reaction, that is qPCR, used for DNA targets. PCR amplification happens and fluorescent dye binds DNA. Signal measurement is done in real time, and it measures how much DNA is present, provides a quantitative uh, data. Next one is a RT-qPCR. It is a combination of RNA and real-time quantitative quantitative real-time PCR. So combination of RNA and quantitative real-time PCR, so that it isolates the RNA first and convert RNA to cDNA and amplifies cDNA with a fluorescence detection, detect RNA viruses, and tells how much viral RNA is present. Next is a comparative analysis between the early era and modern era. In early era, the pathogen understanding was a limited knowledge. We were only focusing on the visible microbes, that were bacteria and fungi. While moving on to the modern era, there were broad understanding about the airborne pathogens, and including viruses, spores, genetic material like DNA, RNA, etc. Airborne pathogens. Airborne detection technologies like collection of airborne particles were done by passive settle plates, simple impingers, low accuracy, only heavier particles were detected. While moving on to the modern era, advanced samplers were brought up, like electrostatic capture, real-time sensors with better sensitivity and viability preservation. Pathogen detection technologies. The analysis of pathogens were done by microscopy and staining in early era. That is, the culture-based methods were very slow and provided only qualitative or semi-quantitative results. While moving on to the modern era, molecular assay, immunoassay, and sequencing provide rapid and sensitive quantitative detection. Time of the results, in early era, it were very time consuming. It used to take days to weeks. While moving on to the modern era, only a minutes or hours are taking. Accuracy and sensitivity. Accuracy was lower in early era, only collectible organisms were detected, whereas in modern era, high accuracy and sensitivity is high, as it detects even low concentration, and non-collectible pathogens. Applications mainly research and basic health surveillance. Modern era public health, mainly application is in public health and environmental monitoring, etc. So in the beginning of my seminar, I have told that I'll be mainly focusing on two main topics, that is electrostatic capture technology and on-chip lamp amplification. So firstly, we are going through the electrostatic capture technology. So the principle of electrostatic capture technology is when a high voltage is applied to discharge electrodes, it creates a corona discharge which produces a free ions and electrons. Aerosol particles will collide with these ions and it will gain an electrical charge. The charged particles are pulled towards the oppositely charged collection plates by Coulomb force, and these particles stick to the collection plates, which will effectively remove them from the air stream, capturing both large and submicron particles with low energy consumption and minimal airflow resistance. Next, we'll go through the governing equation of electrostatic capture technology. They give a theoretical foundation to design and optimize ESP for better capturing efficiency. So first one is the electric field from the applied voltage E equal to V by D, where higher decide how the charging region will be. Lower the electric field, poor charging will be, and higher the electric field, ozone formation happens and safety concern will be there. Applied voltage and electrode speeding must be optimized for the better ESP uh, capturing efficiency. Coulomb force on a charged particle F equal to QE, where it decides higher the charge, higher the capturing efficiency. Poisson's equation from the electric field and charge distribution. It decides modeling the distribution of electric potential inside the ESP, and the particle motion, that is a Newton's law based, determines how fast the particle conjugate how fast the particles migrate and where they deposit. And next one is a drag force, that is a Stokes law. If the drag force is too high, small particles may escape, capturing airflow must be small particles may escape and capture airflow must be optimized. This equation tells us what voltage to apply, what speed to use, and what spacing to use, and what airflow velocity is needed. Next, we'll go through the types of ESP. There are three types of ESPs: wire plate ESP, wet plate ESPs, and tubular ESPs. Wire plate ESPs can capture airborne particles such as bacteria and viruses. It is a lab scale studies, can affect pathogens viability, whereas tubular ESPs similar to wire plate ESPs, but more compatible. Higher efficiency depends on the flow and rate of particle size. Next is a wet plate ESP. High voltage transformer provide a provide necessary voltage. This voltage applies between the two electrodes, discharge electrodes and the collecting plate electrode. That is, the discharge electrode is in negative terminal and collecting plate electrode is grounded and positive. So corona discharge happens, like negative electrode creates a corona discharge when high voltage is applied, and charging particle, dust, aerosols, or biological particles in the stream collide with the ions, and uh, they uh, they uh, they will bring a charged particle. Migration and collection plate charged particles is attracted towards the collecting plate. Wet plate ESP continuously covered with a thin film, which is very suitable for pathogen detection, preserves viability of pathogens. Next, we'll go through the working of electrostatic receptors. High voltage creates a corona discharge which will produce ions and electrons. There are two charging mechanisms, that is unipolar and bipolar. So unipolar charging mechanism means particles are charged only by one type of ion, that is either positive or negative. In corona discharge, if the discharge wires are negative, particle get charged mostly with negative ions, most common in ESP because all the particles of same charge move uniformly to collector, and it is more efficient, whereas bipolar is less efficient compared to the unipolar charging mechanism. So airborne particles collide with ions and it will gain charge. And charged particles will move towards the oppositely charged collection plates, and the collection plates stick to the plates or liquid films, and the collected particles stick to the plates or the liquid films. There are two stages of ESP, one stage ESP and two stage ESP. In one stage ESP, the charging and collection section happens in a single stage, and two stage ESPs, the charging section is in charging happens in one section and the collecting happens in another section. Next, we'll go through the experimental and simulation setup of electrostatic capture technology. So, a small lightweight two-stage preceptor operating at a 5 to 6.5 kilovolt with the interleaved collection plates. The aerosol size range will be from 0.3 to 1 micrometer. It is this experimental analysis is tested for 0.3 to 1 micrometer aerosols at an airflow of 120 meter cube per height with a low pressure drop. So this diagram illustrates this diagram an ESP prototype which was used for the experimental setup. So from the experiment we have obtained some results. That is, a simulation was validated with the experiment data for 0.3 to 1 micrometer particles, confirming the accuracy. Efficiency was lowest at 0.3 micrometer because of the 0.3 micrometer, as the particle size is very small. The efficiency was very small, very low at the 0.3 micrometer. As the particle size increased, the efficiency also increased with that. Higher the airflow, we have observed that if the airflow is high, the efficiency will be lower, and it is best at 0.6 to 0.8 meter per second. And if the applied voltage is high, the efficiency will be high, and it is best at 6.5 to 6.7 kilovolt. And the optimal range, the performance we have obtained, that it is best at 63.9 to 99.7%, and optimal performance range is approximate 98.4%. So from the figure we can see a simulation parameter we have used for it was illustrated in the figure, and it is a comparison model which is given below. This is the ESP collection efficiency for the graph illustrates the ESP collection efficiency for the particles of 0.1 to 0.1 to 0.5 micrometer at different voltages and flow speeds. And we have seen that optimal ESP collection is 98.4%, and it is best at 6.5 to 6.7 as determined through a MOGA, that is an experimental setup. And the third graph illustrates the ESP collection efficiency under an optimal condition at 0.7 meter per second flow speed, and the applied voltage is 6.7 kilovolt. So the factors and limitations in virus collection using ESP. The factors affecting the virus collection in ESP was the particle size, the charging mechanism, airflow velocity, if the applied voltage is low or the current applied voltage is not applied, then it will affect the capturing efficiency, ESP geometry, and the humidity and environmental condition. And the limitations of ESP for virus collection were lower efficiency for ultra-fine particles, like for 0.3 microparticles the efficiency was lower. As the particle size increased, the efficiency increased with it. The ozone generation, pathogen viability loss. In some type of ESP, the pathogen viability was at risk, and particles re-entertainment and a frequent maintenance needs for ESPs. Next, we'll go through the second main topic, that is on-chip lamp-based detection, a constant temperature amplification using strand displacing DNA polymerase. A constant temperature means 60 to 65 degrees Celsius. A constant temperature is used, and multiple primers enable rapid DNA amplification, and results detected easily by color change or turbidity. Chips layout were designed in Java-based nanolithography toolbox and exported in GDSI format. The diagram illustrates a schematic diagram of a on-chip lamp-based detection for airborne pathogen detection. Next, we'll go through a comparison between the lamp and RT-PCR. In beginning of a seminar, I have told that it is quicker and similar than RT-PCR technique, as a lamp will use a isothermal temperature, that is a constant temperature up to a 60 to 65 degrees Celsius, whereas RT-PCR is a thermocycling, heating, cooling, like that process will be happening. And a lamb is faster, typically faster than RT-PCR. It only takes 20 to 60 minutes, whereas RT-PCR is slower. It will take 1 to 2 hours. The equipment used for lamb is a simple heater, whereas for RT-PCR it is a complex thermocycler. The cost of lamb is less expensive, whereas RT-PCR is more expensive. Detection is through a visual or fluorescence, and RT-PCR is a fluorescence detection. And lamb uses a large number of primers, that is 4 to 6 primers are used in lamb, whereas for RT-PCR it uses only a 2 set of primers. Next, we'll go through the chip design, materials, chambers, and thermal control. So, material and fabrication approaches. The materials and fabrication approaches used for on-chip lamp was PDMS and PMMA. So, PDMS is a dimethyl siloxide, which is a silicon-based organic polymer, which is fabricated using a 3D printed epoxy molds. The channels were of 0.4 mm width and 0.1 mm height. The bonding was done by a oxygen plasma activation plus a thermal sealing at 100 degrees Celsius. Oxygen plasma activation was a prepares the surface, and thermal sealing at 100 degrees Celsius will be bakes makes bond strong, ensure no leakage during the fluid flow. So this diagram illustrates the process flow of fabricating PDMS microfluid chip. Next is a PMMA chips, which is made by CNC milling. That is a computer controlled machinery process. Programmed machine uses a rotating cutting rods to remove materials and create a desired shapes, which is chemically bonded, assisting a thermal bonding at 55 degrees Celsius at a 50 kilopascal pressure, rapid bonding with a good channel integrity. This is an overview of PMA microfluid chip fabrication process. Next is thermal control, a thin film or a micro heater for chamber heating. Closed loop regulation with sensors ensures reliable and consistent amplification. The heat transfer rate equation is delta Q by delta T equal to minus K into A into delta T by delta X. Here K is a thermal conductivity of material and A is a surface area through which heat is transferred, and delta T is the temperature difference, and delta X is the thickness of the material. If the negative sign indicate that the heat flow from hot to cold regions. Next is the chambers. Reaction chamber. There are two types of chambers: reaction chambers and auxiliary chambers. Reaction chambers are micro chambers for DNA or RNA amplification, which is designed for uniform temperature distribution. Auxiliary chambers store reagents or collect waste, etc. Next, we'll go through the experimental and simulation setup of on-chip lamp amplification. The chip design was of PDMS, PMMA or glass micro mixing channels, which improve the reagent mixing. The efficiency was about 98% efficiency. Thermal control, the integrated heaters maintain a constant temperature of 65 degrees Celsius. The detection was a real-time fluorescence or open MV cameras or smartphone based imaging. So the figure illustrates a first figure illustrates the micro mixing of channel, a simple straight channel. Mixing is poor because flow uh, flow remains smoothly laminar. And next one is a molecular units include diamond shaped. Second one is B, that is a molecular units include diamond shaped sections, and the third one is a shear structure, rectangular buffer channel, higher mixing efficiency compared to the straight channels. The middle graph illustrates the stimulating mixing results of fluids in different channels designs, and the third diagram provides a y-axis and x-axis of different channels represent different channel types. At low flow rate, mixing efficiency is higher, and at high flow rate, mixing efficiency is lower. The simulation setup: CFD optimizes fluid flow and mixing. Thermal stimulation ensures uniform heating across reaction chambers, and the molecular dynamics models biomolecule behavior and reaction kinetics. FEA checks chip structural integrity under operating conditions. The advantages of on-chip LAMP detection: it provides a rapid results which delivers detection within 30 minutes, much faster than the conventional PCR, high sensitivity and specificity. Detects very low concentration of pathogens with a strong target amplification and fidelity. Isothermal amplification: no need for bulky thermal cyclers, works at a constant temperature, scalable and cost effective, which is suitable for mass production using polymer substrates like PDMS, PMMA, etc. The limitations were primers and specificity. Designing the 6 primers can be more complex than PCR. It provides a false positives that the high sensitivity of LAMP can sometimes lead to false positives due to non-specific amplification if the reaction isn't carefully controlled. Cost of manufacturing: while the final device is simple, the fabrication of the custom microfluid chips can be complex and expensive, especially for low volume production. Next, we'll be focusing on the integration of ESP with on-chip LAMP. We have in this, I have included the workflow and functional design of the integrated ESP system. So, first the air sampling module. The airborne particles are sampled and corona discharge charge these particles, and they are collected on the collection plate. The nucleic acid extraction, like DNA and RNA, is extracted using a microfluid technique, and on-chip LAMP chamber, that is isothermal amplification, happens in on-chip LAMP chamber where nucleic acid undergo LAMP microheater provide a stable heating, and next is the signal detection and heating. Amplification products are detected optically. So experimental and simulation setup: ESP sampling, high flow rates, flow ESP deposit airborne particles into the collection wells. On-chip RT LAMP, direct amplification in approximate 30 microliter wells heated by integrated microheaters. Test aerosols are SARS-CoV-2 VLP and control aerosols. Blank air, spike positives, and process controls were the controls. The simulation undergoes with the airflow and electrostatics. CFD modeling of ESP chamber. Particle dynamics were done by the Lagrangian tracking of aerosols, deposition efficiency mapping. The illusion modeling was done through the mass transfer estimation of deposited particles into liquid. Thermal modeling, heat transfer of planar microheaters. Uniformity was at 65 degrees Celsius. Reaction kinetics, RT-LAMP exponential amplification model, which provide a predict detection time. Collection to chip integration. Wet illusion extraction. After aerosol collection, the particles are dissolved into a liquid medium, such as a buffer or a lysis solution at the air-liquid interference, which will allow a direct transfer of nucleic acid in the solution to the microfluid chip for downstream LAMP processing. And removable or slidable substrates. Detectable collection surfaces or cartridges can be aligned directly with the chip. This modular design simplifies chip replacement, facilitates seamless handoff between the modules, and reduces the risk of cross-contamination. Next, we'll go through the performance metrics governing equations of the integrated system. Limit of detection, that is LOD. To evaluate the system sensitivity, lower the LOD, system can detect very few copies of DNA or RNA. The equation is mean of blanks plus 3 into standard deviation of blanks by slope of calibration curve. Second one is the time to result, TTR. TTR equal to T of sampling plus T of LAMP, that is time to result. Capture time plus amplification time to show how fast the device give a result. Lower the TTR is crucial for real-time detection. Next one is a capture efficiency, CE. Capture efficiency is represented in terms of percentage. Efficiency and sampling is mainly found through this equation. Higher the capture efficiency, enough sample collected. Next, we will go through the performance evaluation and analysis of the integrated system. The summary of findings were: the combined electrostatic capture and on-chip LAMP amplification creates a viable real-time solution for detecting airborne viral pathogens. The benefits of the proposed system is: the system offers a rapid, portable, automated on-site pathogen detection with high sensitivity. The limitations and improvement areas for the integrated systems are specificity, quantitative analysis, and environmental factors. They can be used in public health and safety, hospitals, clinical deployment, and integration with HVAC systems. So here I present a comparison of electrostatic receptors, on-chip lamp, and the integrated detection approach. So the objective of the electrostatic receptor was to capture airborne particles, airborne viruses efficiently. For on-chip lamp, the main objective was to rapid genetic detection of pathogens from the pre-collected samples, and the integrated system was to combine airborne viruses captured with rapid on-chip detection for real-time monitoring. Methodology was optimized ESP design with a control voltage, flow rate, and electrode geometry. For on-chip lamp, the microfluid chip fabrication from PMMA, PDMA chips, and a lamp amplification. For integrated system, the methodology adopted was the integration of ESP for sampling and microfluid lamp chip for immediate amplification and detection. So, from the key findings of electrostatic receptor, we found that high removal efficiency of aerosol viruses were observed. In on-chip lamp, it provides a rapid sensitive detection, and in integrated system, real-time detection, which combines a high capture efficiency with a rapid detection of the pathogens. The key findings also provided that the electric field was 1 to 3 kilovolt per centimeter, and the column force was 1.2 to zero point 0.2 into 10 raised to minus 12 Newton for 0.5 micrometer particles, and the drag force was 3.5 into 10 raised to minus 13 Newton, and the collision efficiency was 95 to 98% for electrostatic receptors, and the heat transfer rate for on-chip lamp was zero point 0.2 to zero point 0.5 watts for microchamber, and the reaction was completed within 25 to 35 minutes, and the detection limits was about 210 to 100 viral copies. The capture efficiency was greater than less than greater than 90 percentage, and the limit of detection was 10 copies per reaction, and the time to result it taken was approximately 1 hour. The limitations was only capture particles. No molecular detection was done in electrostatic receptors, and in on-chip lamp cannot capture viruses directly from air. They can only detect the pathogens. From the to the integrated system, it was more complex system, requires power source, precise alignment, integration adds cost and design complexity. Uh, they can be used, electrostatic receptors can be used in indoor air purification, infection control in hospital, public spaces, etc. And on-chip lamp can be used in lab-on-chip diagnostic, research and portable detection platforms. And integrated system, real-time airborne pathogen surveillance and outbreak monitoring and pandemic preparedness. Here we can conclude that it is good, electrostatic receptors are good for virus removal but not detection. On-chip is good for rapid detection but not for direct air sampling, and integrated system is the best approach as it combines the pathogen capturing and the detection technologies. The future scope is developing a multiplexed system that can simultaneously detect multiple pathogens, improving the quantitative capabilities of on-chip lamp to provide more detailed information on pathogen load, and integrating the system with a cloud-based network for real-time data analysis and public health monitoring. So here I conclude my seminar with a conclusion that integration of electrostatic capture with on-chip lamp enables real-time airborne pathogen detection. This system achieves rapid, highly sensitive detection with very low limit of detection in portable automated format. This approach supports timely responses in hospital, airports, and other high-risk environments. Towards a portable lab-on-air systems that continuously monitor the environment and provide early warnings of infectious diseases and outbreaks. So these are some of the references which I have taken while preparing for my seminar. Thank you.